Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
If you really stop and think about the human condition, or maybe the scientific condition, it really all boils down to a refusal to be blind. We have this aggressive, almost stubborn curiosity. We just can't accept that something is hidden from us.
Right. It's never enough.
Never. It's not enough to see the mountain range. We have to see the rock.
Yeah.
It's not enough to see the rock. We need to see the crystal lattice, then the molecule, then the atom. It's this insatiable need to just peel back the layers of reality until there's nothing left.
And that drive is, it's pretty much the engine of our entire technological history. You can draw a straight line of ambition from the very first clunky glass lenses back in the 1600s, which were basically just polished pebbles,
Right.
all the way to the smartphone camera in your pocket, which has more computing power than the Apollo missions.
Incredible when you think about it that way.
And you can extend that line even further, out to the James Webb Space Telescope sitting out at Lagrange Point 2. It's all the same impulse. Reveal the hidden structure. We just want to see more.
It is. It's this universal desire for, I guess, higher resolution.
Yeah.
But here's the thing, and this is really the central conflict of what we're talking about today. For the longest time, we thought there was a hard stop.
A wall.
A physical do not enter sign put up by the universe itself. We assumed that as you try to look at smaller and smaller things, specifically when you're using light to do it, you eventually hit a fundamental boundary, a wall where the picture just goes blurry, and no amount of zooming in is going to fix it.
That's exactly right. And for a long, long time, that boundary seemed absolute. It wasn't, a failure of our engineering or not having enough budget.
It wasn't a skill issue.
No, not at all. It was a failure of the medium itself. The widely held belief in physics was that the very nature of light prevented us from seeing the building blocks of matter. We are talking about atoms. The assumption was, you cannot see an atom with light, period.
Which is such a depressing thought.
Yeah.
But as you and I both know, impossible is usually just a challenge waiting for the right group of researchers. Because today we're discussing a massive breakthrough, something that happened just a few days ago on January 30, 2026.
It's a really fascinating development. Researchers from the University of Regensburg, specifically their Center for Ultrafast Microscopy, and the University of Birmingham they've effectively smashed right through that wall.
They published their findings in nanoletters, and the headline is, it's essentially this: we can now see the unseeable. They've achieved optical measurements with atomic resolution.
Which, just to be crystal clear, shouldn't be possible. Not if you follow the classical rules of optics. If you open a textbook from, say, 10 years ago, it would tell you this is forbidden.
So today, our mission is to explore exactly how they did it, how they managed to see the unseeable. We're going to look at that impossible barrier they broke, the surprise discovery, and it involves quantum mechanics that acted as the key, and why this changes material science forever.
Yeah, we need to really get into the weeds of how they managed to turn a barrier into a bridge, because they didn't just break a rule here. They, in a sense, rewrote the entire rulebook.
Okay, so let's start with the problem itself. I want to understand the enemy. Why can't I just take a really, really strong microscope and zoom in until I see an atom? We have powerful lenses. We can see bacteria. We can see cells. What is physically stopping us?
It's not the lens. That's the thing. It's the light.
The light itself.
The light itself. You see, in our daily lives, we tend to think of light as a straight line, like a laser beam or, a ray of sunlight coming through the window.
A ray, yeah.
But fundamentally, light behaves as a wave, and waves have a specific size, a wavelength.
Right, like ripples in a pond have a certain distance between the crests of each wave.
Exactly. Now, let's stick with that pond analogy for a second. Imagine you're standing at the edge of a pond, and you want to detect some hidden object in the water just by watching how the waves bounce off it.
Okay.
If you have a large rock in there and the waves hit it, they bounce back, they scatter. You can look at the pattern in the water and say, aha, there's a rock there.
Sure. The wave hits the rock, it gets disturbed, and I can see that disturbance. Simple enough.
But now, what if you're trying to find a tiny marble, and the waves you're sending out are these big, rolling swells? Let's say they're a meter between each crest. What happens when that big wave hits the tiny marble?
Probably nothing. It just rolls right over it. The marble isn't big enough to disturb the wave at all. It's basically invisible to the wave.
Precisely. The wave effectively ignores it. And this is what we call the diffraction limit. Because light is a wave, you can't focus it purely down to a single geometric point. It always spreads out a little bit. You just can't focus it arbitrarily sharply.
So there's a minimum size to the spot you can make with light.
Yes. And the consequence of that is that conventional optical microscopes, the kind you might remember from high school biology, or even the really expensive ones in medical labs, they cannot resolve structures that are smaller than roughly half the wavelength of the light they're using.
Okay, so let's put some numbers on this to make it real. Visible light has a wavelength of what? Somewhere between 400 and 700 nanometers?
Roughly, yeah.
That's the range. Which means the absolute best resolution you can possibly get with visible light is maybe 200 nanometers.
Best case scenario, yes.
And an atom is?
An atom is typically in the range of 0.1 to 0.3 nanometers.
Okay, so the scale is completely off. It's not even close. We are trying to pick up a single sesame seed with a bulldozer. The light waves are literally thousands of times too fat to feel the atom.
That is the perfect way to visualize it. And that's why, for the longest time, the very building blocks of matter, the atoms themselves, were simply beyond direct optical observation. We literally could not see them with light.
Now, I know what some of our listeners are probably thinking right now. Who cares about light? We have electron microscopes. I've seen those black and white pictures of atoms from electron microscopes. So why is this specific breakthrough with light so important?
That is a really critical distinction. And yes, you're right. We do have electron microscopes and scanning tunneling microscopes that use physical probes. And those are amazing, amazing tools.
But they have limitations.
Severe limitations. Electron microscopes, for example, often require a high vacuum. That means you can't look at anything that's wet or alive or volatile.
So no biology, really.
Not living biology, no. And the high-energy electrons you use can actually damage or destroy the very sample you're trying to look at.
So you get the picture, but you might kill the patient in the process.
Often, yes. And those physical probes, the scanning ones, are very, very slow. They literally drag a needle across a surface line by line.
Like an old dot matrix printer.
A very, very slow one, yes. Light, on the other hand, is fast. It's generally non-destructive. And most importantly, light interacts with materials in unique ways that tell us about their chemical and electronic properties. If we could just see atoms with light, we could learn things that electron microscopes simply cannot tell us.
So the goal has always been this kind of holy grail. Can we get the resolution of an electron microscope, but with the versatility and the speed of light?
That has been the dream. And that is exactly what this team from Regensburg and Birmingham went hunting for.
So let's talk about their setup. They knew they couldn't just use a normal lens because of that diffraction limit we just talked about. So how did they try to cheat the system? What was the workaround?
Their approach falls under a category of science called near-field optics. The basic idea is, if the problem is that light waves are too big when they're traveling through free space, what we call the far field,
right,
the solution is to manipulate the light right up against the object you want to look at.
So you get up close and personal, you eliminate the travel distance where it can spread out.
Extremely close. They used a setup that involves a very sharp metal tip. Now, when I say sharp, I don't mean like a needle you'd sew with. I mean atomically sharp.
Atomically sharp. What does that even mean in practice?
It means the radius of curvature at the very apex of this tip is typically about 10 nanometers.
10 nanometers. Okay. For context, a human hair is roughly 80,000 to 100,000 nanometers wide. So this tip is thousands of times sharper than a single hair.
It is. And the technique involves bringing this tip extraordinarily close to the surface of the material they want to study, hovering just above it.
So they have this nanometer sharp needle floating over a sample.
Yeah.
Then what? Do they just shine a light on it and hope for the best?
Yes, but with a clever twist. They use a continuous wave laser to illuminate the whole system. Now, normally, that light would just hit the surface and bounce off, and you'd be stuck with the same old diffraction limit.
The bulldozer problem again.
Exactly. But because that sharp metal tip is there, something really interesting happens. The system squeezes the infrared light into the tiny gap between the tip and the sample.
Squeezing light. I love that image. It sounds like they are physically forcing the light to be smaller than it wants to be, like putting a corset on a photon.
That's a fair way to visualize it. It's a phenomenon called plasmonic nanofocusing. The presence of the metal tip acts like a lightning rod or an antenna, and it concentrates the light field right at its apex.
So it's a funnel?
It's a perfect funnel for light. It confines the energy. And by doing this, they completely bypass the diffraction limit because the light isn't traveling freely anymore. It's trapped in this tiny, tiny cavity.
So by confining the light to the very end of the tip, the resolution of the picture you take is no longer determined by the wavelength of the light, but by the size of the tip.
Exactly. The resolution becomes roughly the size of the tip's apex. In this case, that's about 10 nanometers.
Which is huge, right? I mean, going from 200 nanometers down to 10 nanometers is a massive jump.
Oh, it's a dramatic improvement. This technique, in its early stages, is called near-field optical tunneling emission. And getting down to 10 nanometers is a massive victory for optical microscopy. It allows you to see things like large molecules, proteins, that kind of thing.
But, and there's always a but in these stories, isn't there?
Always.
10 nanometers is still not an atom.
Correct. As we establish, atoms are generally in that 0.1 to 0.3 nanometer range. So while 10 nanometers is incredibly small, it's still about a factor of 32 coarse to see an individual atom.
It's like trying to type on a smartphone keyboard while you're wearing boxing gloves. You know the keys are there, but your finger, or in this case, the tip, is just too wide to hit one at a time.
That is a perfect analogy. If you scan a grid of atoms with a 10 nanometer wide tip, you are effectively averaging the signal from dozens, maybe hundreds of atoms all at once. The image you get just looks like a smooth surface. You can't see the individual bumps. You can't see the lattice structure.
So up until January 30th of this year, the consensus was essentially, this is as good as it gets. You can squeeze light down to the size of your tip, but you can't really make the tip smaller than about 10 nanometers because, well, metal isn't infinitely strong. You run into physical limits.
Right. You run into structural limits of the material itself. So they had a great microscope, an amazing microscope, but it wasn't an atomic microscope.
And this is where the story gets really good. Because typically in science, when you hit a physical limit like the size of your tool, you sort of accept it and work around it. But this team, led by the researchers at the Regensburg Center for Ultrafast Nanoscopy, they were determined to find the absolute limit.
They wanted to know what happens if you just keep pushing.
So they started moving the tip closer and closer to the surface, just to see what would happen to that confined light as the gap got smaller and smaller.
Yeah, and we are talking about closing the gap down to atomic dimensions here. They are hovering a sharp metal spike, maybe a single atom's width away from the surface.
That sounds incredibly risky.
Yeah.
And what happens if you touch the surface? Do you just crash the machine?
You absolutely crash the tip, you blunt it, you ruin the sample, the experiment's over. It's like trying to fly a helicopter 6 inches off the ground in the middle of a hurricane. It requires an immense amount of stability and precision.
But they did it. They kept reducing the distance between the tip and the sample until it was comparable to the spacing between individual atoms.
And this is where the aha moment happens. I was reading the account from Felix Schiele, one of the lead authors from the University of Regensburg. He described it almost like a shock.
Yeah, he noted that at these very, very small distances, the signal, the light that was coming back from that tiny gap, it just shot up dramatically. It wasn't a gradual increase. It was a massive spike.
And he said, and this is the quote, "We didn't immediately understand what was happening." That is the most exciting sentence in all of science. It's never eureka. It's, huh.
That's weird. That's weird usually precedes either a Nobel Prize or a laboratory fire. In this case, hopefully the former.
Hopefully. They realized that when that signal spiked, the resolution of their image suddenly sharpened. I mean, drastically.
They weren't seeing those 10 nanometer blobs anymore.
No, they were suddenly resolving features down to 0.1 nanometers.
0.1 nanometers, that is the atomic scale. They were suddenly seeing the atoms.
They were. They had inadvertently, accidentally broken the barrier. But the question, of course, was how? Their tip was still 10 nanometers wide. How could a 10 nanometer tip possibly take a 0.1 nanometer picture?
Right. I mean, let's go back to our boxing glove analogy.
Yeah.
How did the boxing glove suddenly turn into a needle? The glove didn't change size.
The glove didn't change, but the physics of the interaction changed. And this is why we're here today. The answer lies in quantum mechanics.
Okay, let's unpack this. This is where we need to be really careful because quantum mechanics is usually where our everyday intuition goes to die. How does a quantum effect turn a 10 nanometer flashlight into an atomic spotlight?
It all has to do with what happens in that tiny, tiny gap between the tip and the sample. Now, in the classical world, the world of baseballs and planets, if you hold a ball close to a wall but you don't touch it, the ball stays in your hand. There is a gap. Nothing crosses it.
Right. Almost touching is still not touching. The circuit is open, no electricity flows.
But in the quantum world, things are, well, they're fuzzier. Electrons, specifically, they have a probability of being in different places at once. They aren't just hard little marbles, they are more like probability clouds.
Okay.
And if you bring two conductive materials close enough together, like the metal tip and the sample surface, the edge of the electron cloud in the tip starts to actually overlap with the sample.
So even though there is still empty space between them, physically, the electron can sort of bridge that gap.
Exactly. There is a non-zero probability that an electron can simply appear on the other side. It doesn't travel through the space, it tunnels through the barrier of empty space. It's a purely quantum effect.
Okay, so we have electrons tunneling.
Yeah.
I've heard of scanning tunneling microscopes, so that part makes sense. But tunneling usually just creates an electrical current. How does that create light? And more importantly, how does it create this super resolution light?
This is where the laser comes back into play. Remember, they are constantly shining that infrared laser on the whole system. Light is an electromagnetic wave. That means it consists of an oscillating electric field. It pushes and it pulls on charged particles like electrons.
So the light is providing this rhythmic push-pull, push-pull.
Correct. This infrared light creates a continuously oscillating electric field right in that tiny gap, and it acts as a driver. This field forces the electrons to leap back and forth between the apex atom of the tip and the sample.
So the light is like a pump, or maybe a conductor's baton, setting the rhythm.
A conductor's baton is a great way to think of it. It drives the rhythm. The electrons are tunneling back and forth, but they're doing it in perfect time with the frequency of the laser light.
Okay, so we have electrons jumping back and forth across this gap in time with the laser. I'm still missing the last step. How does that help us see anything?
This is where the antenna analogy they use in the paper comes in, and it's perfect. Think about how a simple radio antenna works. You drive electrons up and down a metal rod with an electrical signal, and that acceleration of electrons generates radio waves. It generates an electromagnetic signal.
Moving electrons create electromagnetic waves. That's Physics 101, right?
Exactly. Now, in this experiment, the electrons that are tunneling back and forth between the tip and the sample, they're doing the exact same thing. They are acting like a tiny single atom-sized antenna, and their motion produces its own faint electromagnetic signal, a little pulse of light, essentially.
Wait a second, stop. This is the part that I want to make absolutely sure I'm getting. The light that they are detecting. It isn't the laser light bouncing off the atom.
No. And that is the absolute critical distinction. The light they detect is what they call the near-field optical tunneling emission. It is light that is generated by the electron's motion as it tunnels back and forth.
That is mind-blowing. So the laser isn't the illumination. The laser is the engine. The electron itself is the light bulb.
That is a beautiful way to put it. The laser drives the electron, and the electron then broadcasts its own position by emitting light.
Okay. But why does this solve the fat finger problem, the boxing glove problem? Why is the resolution so unbelievably good?
Because quantum tunneling is incredibly sensitive to distance. Exponentially sensitive. If you move the tip just a tiny, tiny bit further away, even just half an atom's width, the probability of an electron tunneling drops to almost zero. It just stops.
So the tunneling only happens at the absolute closest point between the tip and the sample.
Yes. Think about the geometry of the tip. It's a curve, right?
Yeah.
Even though the metal tip is 10 nanometers wide overall, the only place that is close enough to the sample to allow tunneling is the single atom at the very, very apex of that curve. The atoms right next to it on the tip are just slightly further away, and for tunneling, slightly is everything.
So the active part of the sensor effectively shrinks from the whole 10 nanometer tip down to just that one final atom at the point.
Precisely. The rest of the tip is silent. It's too far away.
Right.
Only that one single atom is broadcasting the signal.
Yeah.
That is how they get 0.1 nanometer resolution from a 10 nanometer object.
That is it's incredibly clever. You're using the geometry and the rules of quantum probability to filter out everything except the signal from a single point.
It creates a virtual probe that is much, much smaller than the physical probe you're using.
There was a stat in the research that just completely floored me. Dr. Tom Seide from the University of Birmingham, he was trying to explain the sensitivity of this measurement. He said, and I'm quoting here, just one electron moving over a distance smaller than the size of an atom every 100 cycles of the light
can already produce light that is strong enough for us to detect.
That is absurd. One electron every 100 times the light wave oscillates. I mean, we talk about precision measurement, but that sounds like it's straight out of science fiction.
It really highlights just how powerful this technique is. We're not blasting the sample with high energy to get a signal. We are tuning in and listening to the electromagnetic whisper of a single particle doing its quantum dance.
So what does this all mean for what we are actually seeing? You mentioned earlier that we aren't taking a picture in the traditional sense. If I look at the data coming out of this machine, am I seeing a photograph of a bunch of atoms?
Not exactly a photograph, no. Valentin Birkbauer from the University of Regensburg, he put it really well. He said we are no longer limited by how tightly light can be confined. Instead, what we're doing is directly controlling and measuring quantum electron motion.
Okay, so translate that for me. If I'm looking at the screen, what is the image that I'm seeing actually telling me?
You are seeing a map, but it's a map of probability and conductivity. Because the signal you detect depends entirely on electrons being able to tunnel, it tells you how easy it is for electrons to move at that specific point in the material.
So it's a map of how well electricity flows, but at the level of a single atom.
Yes, you are measuring the material's local conductivity with atomic scale precision, and that is incredibly valuable information. Because conductivity isn't always uniform, especially in advanced materials. You might have defects or impurities or specific atomic arrangements that conduct better or worse than the atoms next to them. This tool lets you see those variations, atom by atom.
The paper says this pushes optical microscopy to length scales, nearly 100,000 times smaller than conventional light-based microscopes. That number is just staggering to even think about.
It completely redefines the field.
Yeah.
We are moving from simply observing the shape of things to observing the behavior of things at the most fundamental quantum level.
Now, here's where it gets really interesting for the people listening who might work in labs or follow technology trends. Usually when we hear about a breakthrough like this, atomic resolution, quantum tunneling, my brain immediately goes to one place. Okay, that sounds expensive. I'm imagining a machine the size of a room that costs $50 million and requires a team of 12 PhDs just to turn on.
That is the standard assumption. And, usually you would be absolutely right. In the past, to get anywhere near this kind of temporal or spatial resolution, you needed what are called ultra-fast lasers.
Right.
And these are incredibly complex, finicky, and very, very expensive pieces of equipment. They produce ultra-short pulses of light pulses that last only for femtoseconds.
And a femtosecond is a quadrillionth of a second.
Quadrillionth of a second, yes. And maintaining a laser that can do that consistently is a nightmare. It's like owning a Formula One car. It's incredibly fast, but it spends half its life in the garage being tuned by specialists.
But I feel a but coming.
But this team did it all with a standard continuous wave laser.
Standard as in?
As in the kind of laser technology that is widespread, robust, and relatively affordable. A continuous wave laser just emits a steady, constant beam of light. It's not pulsing at femtosecond speeds. It's simple.
Why is that such a big deal? I mean, apart from just saving money on the initial purchase.
It democratizes the science. It's all about accessibility. If you need a $5 million laser setup to do this kind of work, then only a handful of elite labs in the world can ever verify your results or use the technique to discover new things.
But if you can do it with a standard laser setup,
suddenly thousands of labs around the world can potentially implement this. It dramatically lowers the barrier to entry.
which accelerates the rate of discovery across the board.
Exactly. The simplicity of this setup, and I mean, simplicity is relative, of course. We're still talking about very advanced optics. But that relative simplicity means this technique could become a standard tool in material science much, much faster than if it required exotic, expensive gear.
So we might see this popping up in university labs and corporate R&D centers much sooner than we'd think.
That is absolutely the hope. The researchers themselves explicitly mention that this simplicity could help make the technique more widely accessible. It's the difference between a tool that only exists at a place like CERN and a tool that can exist at every major research university.
I want to zoom out a bit now, pun definitely intended. We've talked about the how and the what. Let's really dig into the why. Why do we need to see atoms this clearly? What does this unlock for the future?
The source material touches on this, and I think it's the most exciting part. It's all about the connection between the micro and the macro.
Okay, connect those dots for me. What does that mean?
Think about any advanced material you use every day. The screen on your phone, the battery in your electric car, the solar panel on your roof. All of these things have what we call macroscopic properties.
Right. The screen is tough but transparent. The battery holds a charge efficiently. The solar panel absorbs sunlight well. Those are the things we actually experience. It's the user interface of reality.
Exactly. But every single one of those macroscopic properties is determined entirely by what's happening at the microscopic scale, specifically how the atoms are arranged and how they interact with each other and with light.
So if a solar panel isn't as efficient as it could be,
It's often because of something going wrong at the atomic level, right at the moment where the photon hits the material and is supposed to create an electron-hole pair. Maybe the electron gets stuck at a defect in the crystal lattice. Maybe it recombines too quickly and the energy is lost as heat.
so if we want to build better, more efficient solar panels, we need to be able to see exactly what's going wrong or what's going right at that single atom level.
Precisely. This new approach allows scientists to study how materials interact with light at the scale of individual atoms. We can finally see the quantum machinery that drives the everyday world we live in.
It's like trying to fix a car engine. Before, we could only look at the engine block from 10 feet away and listen to it. Now we can basically open it up, stick our head inside the cylinder, and watch the individual valves moving.
And not just look at them, we can see how they're moving in real time. We can measure the dynamics. This is why the center in Regensburg is called the Center for Ultrafast Nanoscopy. It's not a still photo. It captures the action.
How does it do that?
Well, because the electron tunneling is being driven by the cycles of the laser light, the time resolution of the measurement is incredibly high, on the order of femtoseconds.
So we can actually make movies of electrons moving.
In a sense, yes. We can capture the dynamics of how electrons move through a crystal lattice, how they respond to light, with an unbelievable combination of spatial and temporal resolution.
That's just wild.
Yeah.
I also want to give a shout out here to the human element. This wasn't some solo genius toiling away in a basement. This was a deep collaboration between the University of Regensburg in Germany and the University of Birmingham in the UK.
Oh, absolutely. Science at this level is increasingly a team sport. You had the experimental expertise in Regensburg, the people who physically build the setup, create the tip, align the lasers, and you had the crucial theoretical contributions from Birmingham, people like Dr. Tom Seide, Felix Schiegel, Valentin Bergbauer. It really does take a village to see an atom.
It really does. And I have to mention the visual they released with the paper. I know this is an audio format, but the artistic representation they had done by an artist named Brad Baxley is so cool. It shows these bright glowing spheres, the electrons leaping back and forth between the sharp point of the tip and the flat sample below. It really drives home that we aren't looking at static rocks anymore. We're looking at a dynamic, buzzing Gantz of quantum particles.
It helps visualize the invisible. And that is really the core of what this discovery is all about. It changes our fundamental mental model of the material world.
Okay, so let's try to recap the journey we've been on today. This has been a dense one, but I think the payoff is absolutely huge.
We started with the diffraction limit, this old idea that light waves are just too big and clumsy to see something as small as an atom, a fundamental wall of physics that stood for centuries.
Then we introduced the heroes of our story, the team from Regensburg and Birmingham who decided to cheat. They decided to squeeze light into a tiny gap beneath a sharp metal tip using this idea of near-field optics.
And they kept pushing that tip closer to the absolute limit until the classical world gave way and the quantum world took over.
Which led to that complete surprise, that's weird moment. Quantum tunneling allowed them to use a simple standard laser to drive electrons back and forth, effectively turning a single atom into a broadcast antenna.
Resulting in an unbelievable 0.1 nanometer resolution, true atomic vision, and a way to measure a material's conductivity with a precision we've never had before.
And maybe most importantly for the future of science, they did it all with equipment that is surprisingly accessible, which opens the door for a revolution in how we study and design new materials.
It's a classic scientific story, really. You hit a wall, so you figure out how to dig a tunnel under it. In this case, literally a quantum tunnel.
I love that, and I really like the phrase they used in their paper to describe it. Atomic scale telegraphy with light.
It fits perfectly, doesn't it? We are literally tapping out messages using single electrons as the messengers. ...
It really forces you to reconsider what we even mean when we say fundamental limitations.
It does. It's a good reminder that fundamental often just means we haven't figured out the clever workaround yet.
And that's really where I want to leave our listeners today. We all grow up learning these hard and fast rules. You can't go faster than light. You can't see atoms with light. You can't be in two places at once.
And yet, quantum mechanics seems to view these rules more as suggestions, or at the very least as puzzles to be solved in interesting ways.
Exactly. We just learned how we used light something huge and wave-like to prod single electrons, and that those electrons shouted back loud enough for us to hear them. It just makes you wonder, what other impossible barriers are just sitting there waiting for the right trick, the right atomically sharp tip, or the right happy accident to be broken wide open?
Perhaps the limit isn't in the physics at all, but just in our imagination of how to apply it.
A profound thought to end on. Thanks for exploring this breakthrough with us. Keep questioning the limit.
And keep looking closer.
See you next time.